So hello, everybody. I guess you can hear me because I can hear the echo. As you can see, the title for the talk is changed a little bit because Andre complained about the usage of the modern word in the talk titles. I kind of had to recompile my LaTeX presentation to remove the word modern, so it's a new look. Okay, so this is going to be a little bit a strange talk. Fortunately, there are no C++ committee members in the audience because I would probably annoy most of them, including Andre. So I would annoy Andre by talking about concepts, and I would annoy Bjarne and everybody who worked on concepts by misusing concepts. So we are going to cover, let's say, a little bit of a different look on template metaprogramming. So template metaprogramming is something that we have had for a long time. And apart from having a little bit nicer syntax nowadays, not much has changed. I'm going to focus on a different way to look at TMP that will allow you to easily reason about any code that you see that uses template metaprogramming techniques. As usual, the usual disclaimer from Phil Wadla. I'm not going to read it. You all read it, right? This is something that doesn't really apply to template metaprogramming. So if you go to a company and write something with TMP, obviously somebody is going to hurt you really bad afterwards. So take this with a grain of salt. You should usually heed the advice of Philip Wadla, but obviously not in this context. Another quote that I forgot who said it. It was maybe Sean Parent or some of the famous C++ guys. When you try to make something, it's really difficult not to make it Turing complete. So, well, it's usually a surprise that templates are Turing complete language inside of C++. It's not really, because it's really hard to make something not to be. I recently heard that even CSS is nowadays Turing complete. So if a styling language is Turing complete, obviously templates are going to be as well. So the things for what TMP is used, if you want to execute anything during compilation time instead of relying it on being executed at runtime, you can use template techniques. Now, it used to be essentially for all computations during compile time, but nowadays we have const_expr. So most of normal computations, like the usual example of calculating Fibonacci numbers using templates, is not something that you would do nowadays. Nowadays, TMP is mostly used for type manipulation. So either to convert types to types, or values to types, or types to values. You should probably never use TMP nowadays for calculating values from values. Now, people usually say that template metaprogramming is a functional language because it doesn't have side effects and everything else. You shouldn't really trust in that sentence because it would make it the worst and the ugliest functional programming language in the world. So if somebody tells you, well, you certainly love functional programming because you're a C++ developer and you need to know templates, that's not a great pitch for functional programming languages. But if you try to look at TMP as if it was a functional language, maybe it would make it easier for us to understand it. So in a nutshell, the whole concept is that when you see something that is called std vector, until you get into runtime, it's not a collection. It's just a function. So it's a function that transforms one type, for example, an int, into another type, a vector of int. So whenever you see something from standard library, which usually you think of as a class or a structure or a collection, in this context and in the context of today's talk, it's a function. I'll usually just say function and not meta function because we are only talking about functions during compilation time. In C++, since TMP was, let's say, discovered, we had one ugly syntax to define template meta functions. Nowadays, we have at least 3 or 4 different syntaxes, which is cool, right? The problem is that everybody hates the syntax of TMP. So with each new version of C++, we get a subpart of C++ that tries to aim how to fix particular subpart of TMP. So one of the, let's say, cool new things that we got is the using declaration. And if we want to create a function that converts one type to another, we can just say, OK, template type name T, and say using, then function name, and then how to calculate the result of a function. So this doesn't look like a function, right? It looks like a using declaration. But just try to blur your vision. If you blur a bit or squint so that you don't really see template, using, or type name, or anything else, the type name T is a function argument. Squint. Nobody is squinting. Squint. And obviously, the inner type T is a function name, and value type is the function result. How are we going to calculate the result when somebody calls the function with a specified argument? And in the same way, not much squinting is needed for this one. This is a function call. For this, you just need to squint a little bit so that these brackets go into parentheses. Right? So for all of the slides, just try to read them as if it was normal parentheses and not these ugly little things. So this is the Terse syntax. If you just want to define a simple function that evaluates to a type expression on the right-hand side. We have the old syntax, which I decided to call a general syntax, because it allows us to do a little bit more. Instead of using the using keyword, now a function is defined by class keyword or a struct keyword. Again, a strange keyword to define a function, but again, squint. So in this case, we are defining a meta function that, again, takes a function argument. It has a name, and obviously, it has a result. Now, the difference between the previous and this one is that now we have a named result. So when we want to call a function, we would call it like normal with these parentheses, strange parentheses. And if we want to access a specific result, we just say : type. OK? And we can make it a little bit more complex. We can return types. We can return values. In this case, we are returning one type and one context per bool, which detects whether the type T, the collection type, the type that a collection contains, is the same as a type that we expected. Now, this is something that we don't have in normal C++. If we write a normal C++ function, we cannot return a collection of values that are named. The most that we can do is to return a pair or a tuple or something else, and then to rely on the callee to know exactly what .first means, what .second means. So in a sense, TMP is even better than regular C++, because we can just all of a sudden decide this is not a function that returns a single value. It returns a multiple values, and we are giving them the names, which is really cool. So when we want to access the values, so named function results, we just call a function and write : type : value. Just imagine if we were able to do this in normal C++, to have anonymous classes, where we can just, like lambdas, return a collection with named fields. That would be freaking awesome. And we have had this since C++ before 98 in TMP. And that's the reason why TMP is much better than regular C++. It just has awful syntax. Now, because of the awful syntax, what you'll find usually in C++ standard library as of 14 and 17 is that all the generalized template functions also come with Terse versions. So instead of forcing you to always write expect inner something something colon type and type def and everything else type name, the standard library provides you with _t to access the colon type and _v short, let's say shortened versions, to access the value. So in the standard library, you have the is_same, which checks whether two types are same, and then you have is_same _t to return true type or false type, and you have is_same v that returns a normal value, true or false. Fine? So, as I said, the reason to use TMP is not to calculate Fibonacci numbers. It's not to calculate factorials. It's to transform types primarily. So to calculate a new type from the old one. So let's see a little example. You want to write a sum function, which will obviously be implemented through std accumulate. But the question is, if it passes just a collection, what's the return type of the sum function? Okay, so one approach is to add an initial value and to deduce the return type from the initial accumulator type, which is what std accumulate does. But what if we want exactly this as the API? We need to be able to deduce, if we have a collection, what type is stored inside of that collection. And for that, we can use exactly the function that we already created, inner type t. So again, squint a little bit. We have if you look above the function signature, we have the template code, template metaprogramming code, and below the name of the sum function, we have normal C++. And until we switch to const x per if, this will be the usual split. Everything that is above the function, the C++ function, normal function name, is template code, and everything below it is normal C++. So what we are saying that we are accepting something C, which is not defined by default. It will be defined by the callee. And then we want to calculate a couple of values that depend on the C. Fine? And we just say, OK, C is not known. Let's say uninitialized. It will be initialized when the function is called. And we have val equals something. This looks like a normal programming language, right? And we have a function call. So we are just assigning the result of a function to some variable. And obviously, then we can use that variable later on as the result of the sum function. So as soon as you see something that has a lot of these, just try to read them as normal functions. So the question is, we have defined the inner value to use the, let's just switch a bit, to use t : value type. And value type is a nested type definition that exists in all C++ collections, in all Qt collections, in all Boost collections, etc. But the question is, what do we do about collections that don't have the value type nested definition? What are we going to do then? All collections, again, all normal collections, should be iterable. So we could probably get the type by finding an iterator for a collection and then dereferencing the iterator. And we again have syntax for that. We can say inner type t is no longer what it used to be. It's now a decal type of what std_begin returns when it's dereferenced. What's the reason to use std_declaval? OK, I need an instance. So it's either t open close parentheses or curlies, which would rely on t having a default constructor. Or if we just want to be as generic as possible, we can use declaval. Declaval is not something, the result of declaval is not something that you can use during runtime. It's just pretending to construct an instance of t. So we are creating an instance for a collection, creating begin iterator for it, and then dereferencing. Does anybody see a bug with this? Yep. So we're dereferencing the pointer, the iterator. And at some point, we might think that this is the same function as before, but we'll find a bug. And when we find a bug in our template code, we usually want somehow to print all the involved types. A little trick that you can use if you don't use an IDE, and you want to find out the exact return type of some meta function call, you can declare a class template called printTypes, which is templated on a variable number of template arguments. You're not going to implement this class. You're just going to declare it. And then whenever in code, you just write printTypes, and this looks like a normal function call, right? So printTypes and list all the types that you want to have printed. When you try to compile it, GCC will any compiler will immediately print out all the types that are involved that you wanted to print. Now, one of the cool things is that the first result is completely surprising. So usually, because we all know that vector of bool is special, and that it doesn't really have a reference to bool, but everybody assumes that the result here is going to be some wrapper type for the inner thing in bool, in vector of bools. But strangely enough, our inner type T with the previous definition works perfectly for vector of bools, which is the special bad kind of vector, and doesn't work with any other normal types of vector. So as previously mentioned, we can use either decay, or we can use remove cvreft, which has been added in recent years. Now, this function is going to work correctly for all collection types that have iterators. Now, the question is, what is better, to use value type or to use dereferencing and decaying and removing cvref? Okay. Okay. Although you are going too much deeper in detail than I wanted. So what I wanted you to answer here is obviously, if a collection says that it defines value type, you should trust it. So if somebody defined it as a nested type def, he or she wants you to believe that that collection has exactly the values of that type. And I would say only as a fallback you should go to this definition. Okay? So by default, trust the implementer, and as a fallback, rely on iterators. Now the question is how to specialize on these two different behaviors. Okay, switch. Now we got another beautiful, minus 2 years ago, we got another beautiful syntax for defining meta functions. And in this case, this syntax is for meta predicates, so meta functions that return bool. And now the keyword that is used to define these meta functions is concept. Obviously, I had to put the note, this is not a proper concept. If some of the people like Bjarne ever sees these slides, I don't want to get into trouble or something. So this is not a proper concept. Concepts should model a lot more than just test whether something has a value type. So what we can do is just say concept or bool meta function requires that C has the type name nested type called value type. Has value type is going to be true if this is satisfied. It's going to be false if it's not satisfied. So it's almost as if we wrote const per bool has value type instead of concept. Okay? In the same way, we can define meta predicate called has begin iterator. And if something has std begin of that, and it can be dereferenced. Let's call it has a begin iterator. We can now use it to implement different sum functions. So the first sum function accepts any C as long as that C has value type. And at the same time, the second one requires that the first one failed, and the second one is it has begin iterator. Now the question is, does this code look nice? In essence, if these functions were standalone, then it would be kind of cool to have template and requires. But the problem here is that for each of the next sum implementations, we would need to negate all the previous predicates and then implement the new specialization for sum. And obviously, not so useful if const expr. We can just say inside of a sum specialize just the part of the function that we need to specialize. Fine by now? OK. And obviously, the full implementation, let's skip that. Or not. So this sum function, what's the return type? Obviously, if you replace the ... with return std accumulate and so on. So we would still need to, when we want to call std accumulate, we would need to initialize, to specify the initial value, which would need to have a type. So we would, again, even if we has value type, we would need to call t : value type in the first case, and in the second case, decal type of blah, blah, blah. So it's not really that pretty. But the cool thing is that the auto part, it will be automatically deduced from whatever we write in the function body. And we can switch to the most modern version of TMP programming, and the only version that actually uses C++ language, normal language. So we can create a function which is not a function that you will ever call during runtime, but it does look like a normal function. What we are going to say is, if const expr has value type, so if we do have the t : value type, we are just going to return decal value of that guy. And if it doesn't have, but it has the begin iterator, we are just going to return whatever the begin iterator points to. Again, it can be an empty collection, it can be anything, because we are not calling it at runtime. At compile time, it doesn't matter whether there are actual values inside of the collection. And else, we are just going to static assert. If there is no value type and no iterators, then we can't really deduce what's inside of the collection. If we wanted to write this in a Terse syntax meta function, we can just say using inner type and then decal type of this helper function we already created, and we got a proper, beautiful template metaprogramming meta function that we wanted in the first place. So we have seen a couple of different syntaxes to write TMP. We can even, when we define meta predicates, we can combine calling normal template metaprogramming functions, and we can combine the requires clauses. So you can just imagine that requires clause is a new way to write predicates, but we can combine them with the old predicates that we already had. Now the huge issue with concepts. Even if concepts and requires have become a part of the standards in -2 years ago, no compilers really support them. GCC pretends to support them, and it supports a lot of these things, but let's say at least 3 of the slides that I've had wouldn't compile with the newest GCC. So the question is, we have a lot of beautiful functions. We have ideas from concepts and everything else, but we can't use them because we can't compile them. What can we do? We can take a step back, because again, concepts arrive in -2 years. Well, arrive in 2 years, have arrived in -2. we now need to take a step back and move ourselves to C++ 17. And in C++ 17, we have the most beautiful meta function that was ever invented. And it's really trivial to define, and it's really trivial to use. You just write void t and pass it some type, and it will return void. Really trivial, right? So void t of int is going to be void. Void t of int, float, string, float, pointer to something, it's going to be void. Really useful function. It always returns a single type called void. Now the point is that the result type is not why this function is useful, because it's always void. The useful part is that it can fail. So if any of the arguments is not a proper type, the compiler is not able to deduce the type, then the whole void is going to fail. And it is going to trigger the spin. It's not going to be a compilation error. It's just going to remove the current overload from the overload set. So we can do something like this. Usually, especially in the old days, when you wanted to write more complex meta functions, you would write a couple of cases with pattern matching, etc., etc. And that's going to be the same with void. By default, if you want to detect whether something has an std type def called value type, by default, we are going to return std false type. This is fine so far. And if, in the second case, if void t of type name t : value type returns a value, in that case, our has value type is going to inherit from true type. So what's going to happen? If you try to invoke this meta function with an int, it will check, can I instantiate the first solution? Obviously, no failure there. T is going to be int, void t returns void, everything succeeded, so I'm going to inherit false type. Then the compiler will try, OK, can I instantiate the second one with int? It will try to see, OK, what does void t of int : value type return? Int : value type doesn't exist, so the whole void t goes away, and the whole second overload or specialization goes away. So the only thing that remains is the first one, which inherits from false. So obviously, int doesn't have value type. In any other case, when we have some collection, like std vector, both of these are going to be valid. The second one is the more specialized one, so the compiler will pick the second one. So for std vector, we are going to have std true type. Cool? We can then use this with if const expert just like we used the concept-based ones. We can even combine a couple of, because we've seen that requires clause allows you to test whether something has operator, dereferencing, etc., etc. So you can test multiple things at once, and you can do the same with void t. So you can just write void t and a couple of decal types for the things that you want to test. Good so far? OK. Now the question is this a little bit too much boilerplate? For each of the, let's say, trait tests, we need to write 2 meta functions. And usually they're the same. The first one is the false type with empty void t, and the second one is tests for a single feature and returns true type. Whenever we have something like this in normal code, we would write, for example, just imagine you want to test whether a collection of items satisfy a certain predicate, whether items in a collection satisfy a predicate. You would write a generic function, so you would write a higher order function that accepts a predicate and calls the predicate on each of the elements. Like, for example, std partition, std count, countif, and findif, etc., etc. So they're all higher order functions that accept another function as a predicate, right? So can we create higher order meta functions? as a hint, I was nodding. Now, this is going to be even worse syntax than everything else. So in normal generic programming, as soon as you want to accept a predicate as a function argument, you're going to create a template function. That's fine, right? If you have a template function, so meta function, template meta function, and you want to make it a higher order function, what are you going to do? Well, add another template to it. So if you want to have higher order meta functions, you just need to use the template thing. And this is the worst thing that I've ever seen in C++, the idea of template. But just stop seeing it as some strange thing. As soon as you see a template inside of a template, just close your eyes and imagine, OK, higher order meta function. OK? So in this case, we are implementing the same thing that we had with void t. So the base case, we are going to inherit, in this case, not inherit, but having value underscore t to be false type. We are going to accept operation, which is the predicate with arbitrary number of arguments. That's the reason for type name ... And when we want to call that operator or that meta predicate, we are going to pass it a series of arguments saved in args. And this is something that has been added in C++ 17 to the standard library. Now, the detector meta function is just exposition only, so you shouldn't use it directly. It's just an implementation that, again, has a couple of useful wrappers around it. And in the second case, we are going to return true type if we are able to call void of op of all the arguments. So as I said, op is a predicate that we are going to call for the arguments that are passed. If that op is valid, then we are going to take the second specialization, and if not, we are going to stay with the first one. There are a couple of useful functions defined, and these functions are something that you should use from the standard library. The first one is detected. You can pass it something that you want to test for, and it will return true or false whether that thing is present in the class that you're testing or not. At the same time, you have the detected t, where you, instead of returning true or false, you're going to get the exact type that is the result type of your operation. So for example, we can create a tester whether something has a non-member begin function. We can just say decal type of, can we call std_begin on an instance of t? OK? And instead of doing all the things with void t, we can just say if const expr, if is detected, if non-member begin is detected on string, do the following. And this code kind of became readable. Obviously, the words are a little bit jumbled compared to normal English language, but this is something that everybody should be able to read and understand, right? The same for non-member end, and we can combine a couple of results inside of a single const expr. So we are testing whether something has a begin and whether it has an end. We can do something even more. So we have tested whether collection has the begin iterator and iterator. The next thing that we want to do is to test what the begin is going to return. Although I have a mistype, it's not free begin, it's non-member begin. So we are going to try to detect whether stud string has a non-member begin, if not, a non-member begin can be called on a stud string. And we're going to get the result type of it. Then we are going to dereference it, check whether it can be dereferenced, and if it can be dereferenced, we will get true, or otherwise we are going to get false. Okay? Now in the case that it wasn't a stud string, but something else, what would happen here is that detected t will return a really strange type called non-such. and after that, is detected v is not going to be able to dereference the non-such type. So the whole expression will just return false. And now we can even improve on this. We can check whether the iterator has increment operation, or not only iterator, we can check this for any other type. We can check whether something is copy assignable, and then we can define a concept without actually having concepts in the language. We can just define context per bool. Something is input iterator if it can be decremented, dereferenced, and copy assigned. Obviously, the input iterators have a few more requirements, but this is sufficient for now. We can then test whether a couple of more things. For example, we want to check whether our type is equality comparable, which means that it needs to support two operations, equals, equals, and not equals. So this is a concept, right? Equality comparable is a concept. So we have, again, defined a concept just using the detection and void t. And again, we can define whether something is in input range, etc., etc. And there are a couple of more useful functions in the standard library. You can check it out. Currently, GCC supports this in std experimental namespace. I'm not sure whether they pushed it into proper STL. And maybe even libc++ from Clang supports it. I'm not sure about Microsoft's compiler because who cares? Well, have you seen the previous talk by Anton Polushkin? So I have the same opinion regarding Microsoft Visual Studio as he does. When he got asked the same question, well, he kind of answered the same. He said, the thing that I tested works even in Microsoft Visual Studio, so I expect it to work in all the compilers in the world. I'm a little bit more depressive than him. I really don't care about Visual Studio at all. So if it doesn't work, then, well, you can implement it by yourself.
Now you can actually use Clang with Visual Studio, so you don't have to be depressed.
OK, so Goran said that if you have to use Visual Studio, there is a remedy for that because nowadays Visual Studio also comes with Clang. Is it using libc++ or? OK, so Clang with Microsoft's STL. Nice. OK, so I think this is all from me. And obviously, the last slide, thanks to a lot of people. And I finally got my book printed. OK, so the question is, thanks for the sign. The question is if this is possible with C++ 11 or 14, not with the same implementation. So there was a core working group issue regarding something with void t. If you are in C++ 14, you will need to define void t with a little bit more code. So most of the ideas can be ported, but as it's usual with C++, if you write TMP and try to port it to an older compiler, the code just doubles with each new jump to a previous version. And it's the same here. So everything here should be easily implementable in C++ 11, but I don't think that anybody wants to do it. Now just the thing. Can you pass the book to, well, I can pass it. Here you go. More questions? Sorry?
I got a microphone for the questions. Anyone? No questions?
Can you go back, please, a couple of slides for the bigger part?
Wait a sec.
I'm just asking to go back to, just one, next one. Yeah. I mean, I did not get here the decal type for the assignment. So the decal type would return what the assignment would return. Am I right?
The second one.
Yes.
So what's the exact question?
What the decal type here would return? What is the copy assign? Is it a search-in now? Or is it like a meta function, as you said, would return a Boolean? Okay. Or what? I did not get it here.
Decal, you don't really, you shouldn't think of these as returning a value.
Okay.
I forgot to mention that. So all of these, let's say, detectors that are used with is detected.
Yes.
Just think of them as something that either passes or fails.
Okay.
And then is detected is going like throw and catch.
I see. So they are used in combination with the other. Okay.
So just to repeat, these little detectors, don't think of them as returning values. The only thing that you should consider with them is in a normal programming, they're either succeeded or they throw an exception. And then the is detected will check whether something succeeded or thrown an exception. Okay?
Okay. Not standalone to use.
It's not a standalone thing.
Yeah. Can you go to the next slide?
Yep. Can you pass the?
Thanks, man.
No problem.
Thanks.
Okay.
Is this the next one?
Yeah. I just have a question about equal compare. Do we need to have both equal and not equal?
If you want to write a concept, then you're, obviously according to Bjarne, you should write a whole concept. You should describe an idiom, not only test a single feature. So if you want to say something is equality comparable, it should have both equality and inequality in mathematics and in normal life, I guess, so as well.
Not in the standard, yeah? Not in the standard. The standard does not really force to have inequality.
Yeah, of course.
Yeah.
So the standard doesn't force it, and that's the reason why we need to check it.
Yeah.
Yeah.
Thank you.
Okay. Do you have my book? Okay, because you also asked a question. Okay, if you didn't ask, if you don't want my book, who cares? No, this was really insulting, right?
I have a question regarding this EQ compare.
Just a question.
If you're trying to make it more complete, why wouldn't you also try to switch the arguments, like U to the left and T to the right? Like
can you repeat? I missed most of the sentence.
You said that you want to have inequality also because it's in mathematics you'd expect that, but in mathematics also it's commutative, so you should also, in my opinion, check U on the left hand and T on the right hand.
Okay,
side.
This is the most awful question that I've heard, and you're completely right. So you get the last book. Yeah, of course. If you want to check, yeah. I guess I should have just written equality comparable on T and not T and U, and then it wouldn't be a problem. And now there are no more questions because there are no more books.
Are there any production-ready libraries with hierarchy of such concepts suitable for, using a standalone library?
Just a question, where is the, okay. So ranges V3 from Eric Nibler. And now, whether he's using the detection idiom or something else, I haven't checked. But he did a lot of work to kind of hack concepts into his library. And there are a couple of more that are not that complex, but I don't know them on top of my head.
As I know, ranges v3 is still in development, and the API can change, isn't it? No, I mean, library.
I didn't understand you.
Ranges v3 library, is it, does it have stable API? No, I mean, as I know, it said that API can change and
yes, but not that much. So while officially ranges v3 is unstable, most of it, at least most useful parts, are kind of fixed already because they have been proposed for the standard. The only changes that are current, I think even at this exact point being made, is now Eric is synchronizing the changes they made for during standardization to backport them into ranges v3. But mostly the normal API, the usual API, stayed the same. I haven't seen any significant changes.
Yeah, thank you.
Do you know if there's any resource where you said that with each C++ standard iteration, there is a better way of doing these things? Is there a resource that basically lists all of them to see how they have changed throughout time?
Not that I know of. You can ask Andre. Especially when we get static if, then we are going to get yet another, let's say, useful syntax for templates. So somebody should write a book.
Okay, thanks.
No more questions?
Okay. I have the book already, yeah, but I'm just asking more. I just would like to come back to this point here of comparability. Maybe we can take it offline. I don't want to book all the time for that, but I'm also wondering, because somebody asked about the U and V types, why you have why you have two? I mean, usually it's just comparability against one type, and a plus usually it's with references. So I'm not sure how you handle all of that. I mean,
to be honest, this, let's say, concept is not something that is used. It was just made for this presentation.
I see.
And I really didn't think about commutativity and everything else. And obviously, in normal situations, you would write equality comparable on T and just check for a single type. Yeah. Although I did think a little bit about it. I did say U is by default T.
Yeah, but it can be different.
Yeah, of course. Okay. So you're free to go. Thank you.